Hi everyone, this is going to be the second class in computer architecture lecture series, and we will be discussing evaluation metrics today in a quite brief manner. More details will be provided in lecture hours and handouts. The evaluation metrics come quite handy when we compare two computing machines or two central processing units, or in general two complex architectures. Although we will be dwelling on the CPUs and computation costs and performance, most of these metrics will be applicable to many more fields of engineering. So let us start with the question, how do we evaluate performance? There are four well-known evaluation metrics: cost, performance, power, and reliability. And it is much more effective if we consider them all together. The most known combination include performance cost and performance power. Here, the IPS stand for instruction per second. Therefore, the unit of the performance cost evaluation metric would be instruction per second per dollar, for example. These metrics might be important for making design and purchasing decisions. There are two types of cost: unit cost and startup cost. Unit cost consists of manufacturing integrated circuits, so the chip cost is proportional to silicon area used. However, assuming a uniform defect density, larger chips mean less working chips. Because even if a single transistor is bad, the whole chip might be useless. The other type of cost is known as the startup cost. This includes the manufacturing as well as research and development costs. For instance, suppose that we use 500 engineers, each at about $200,000 per year. This makes about $100 million investment for the design of the chip architecture. On the other hand, fabrication of the chip requires clean rooms, lithography, and testing equipments, together of which can cost up to about $2 billion. So if you sell 10 million chips, startup costs will amount about $210 per chip, and without even considering the unit costs. Therefore, chip manufacturers do not make a lot of money per chip, but their aggregate sum of revenue makes it sometimes profitable. As for the performance, we will introduce two definitions. One is called latency and the other is throughput. The latency is measured in terms of execution time, and throughput is usually expressed in terms of bandwidth. But which definition we will choose when we compare complex systems? Maybe both of them. Maybe one definition is more valuable than the other, depending on the context. Let us consider an example. Consider two cities, A and B, 30 miles away from each other. Car's capacity is 5 people, and it moves with speed at 120 miles per hour. The bus's capacity is, on the other hand, 60 people at a speed, and it can move at about a speed of 30 miles per hour. Let us find the latency and throughput of these vehicles. Latency is the time it takes to travel between city A and city B. So the car takes 15 minutes to travel, and bus takes 1 hour to travel the same distance. The throughput, on the other hand, depends on the number of people each vehicle is able to carry at a given time. If we look at it carefully, we can realize that car can travel from city A to city B and come back and travel the same distance again to carry 5 more people. At the end of 1 hour, it can only carry 10 people straight. Bus, on the other hand, can only travel from city A to city B once and is able to carry 60 people during 1 hour time period. This makes bus's throughput 60 people per hour. So the natural question is, which one is faster? Before we answer this question, let us talk a little bit about performance improvement in terms of latency and throughput. For instance, let us assume that we have two processors, A and B, and both run a program called P. We needed to choose a particular program here because otherwise there will be no criterion to compare against these processors. So if the processor A is sometimes, maybe R times faster than B, then their latency of A is R times less than the latency of B. This implies processor A is R times faster than processor B in terms of throughput. So going back to our car bus example, in terms of latency, car would be 4 times faster. And in terms of throughput, bus would be 6 times faster. So depending on the metric that we're talking about, the number R can be changed. Therefore, depending on the evaluation metric, the number of times one vehicle is faster than the other changes. Same argument goes with the processor or DRAMs or other computer components that we will be examining in this class. Let us also touch upon one of the most fundamental performance equations within the context of computer architecture. The latency of a processor A, expressed in terms of seconds per program, can be decomposed into 3 distinct product terms. These product terms are instructions per program. The second product term is cycles per instruction. And the third product term is seconds per cycle. Instruction per program is a function of the program itself, of course. It is also a function of compiler and the ISA. Cycles per instruction, on the other hand, is a function, actually a strong function of a microarchitecture, but it also has some kind of dependence on the compiler design and the ISA. Seconds per cycle is a function of microarchitecture and technology parameters. So the objective of this equation, or the designer, is to minimize the latency, the delay in the system while running a general program. The challenge is that these 3 product terms play against each other. Let us consider the last 2 product terms, namely cycles per instruction and seconds per cycle, to compute the seconds per instruction. If we take the reciprocal of this metric, we get a very popular known metric called instructions per second, abbreviated as IPS. Consider the following example. Let us have a CPU with a CPI 2. Clock frequency of that CPU is 500 megahertz. Therefore, the IPS can be computed to be 250 million. If IPS is one of the performance metrics that people historically use to compare performances, yet it may inversely vary with performance. This means if various optimizations add more instructions or different ISAs generate different number of instructions, IPS value may not be able to measure the true performance. So some people proposed floating point operations that goes with the name flops in replacement of IPS, owing to the fact that most of the floating point operations cannot be optimized, and they actually possess the longest delay most of the time. Though there are counter arguments to flops, supporting it with most of the operations are, for example, integer, etc. So they're like counter arguments. So that made IPS one of the well-known and widely used and adapted metric when people compare 2 CPUs or 2 processors. So let us consider, the following example to quantify what we have learned so far. Imagine a processor with the following instruction frequencies and costs. Integer ALU, 50% of time it takes 1 cycle. Load operation, 20% of time and 5 clock cycles. Store operation, 10% of time, 1 clock cycle, and branch operation, 20% of time, 2 clock cycles. So the question is, if you have 2 changes labeled as A and B, and A is basically one change in that base system, the reduction of branch cost to 1 clock cycle. The B change is about reducing the load cost to 3 clock cycles. So question is, which one of these changes, when they are applied independently to the base system, will help improve the performance the most? Let us first understand that we need to compute the average CPI of the base system as the first thing in our list. This computation is easy to do. As you might remember from our probability classes, the average is given by the expression shown below. The computation of that average yields 2. If we apply the changes in two different scenarios, we will end up with the average CPI for the change A to be 1.8 and the average CPI for the change B to be 1.6. So the change B would be the preferred change if we are to allocate money, time, and human workforce. Energy and power is another important metric widely considered and taken into account designing complex circuits and computers in particular. It is known from physics of electronic components that wider transistors and shorter wires reduce resistance. Reduced resistance will decrease the power consumed per unit time, and this is expressed in terms of watt per second. There are also other definitions of this metric, such as power density, and this definition is expressed in terms of watt per centimeter square. The power is usually dissipated in the form of heat, and this heat also increases the temperature. The increased temperature increases the resistance of electronic components, which in turn increases the power dissipation. This cycle is known as the thermal cycle, and maybe is one of the most widely known technique to deal with this problem is the cooler supports. The cooler basically supports the whole hardware to reduce the temperature down. Finally, let's consider the means and ways of transistor scaling effect on the power dissipation. For example, shorter wires, smaller transistors, they decrease the resistance and capacitance, but smaller capacitance also increases the leakage. Also, increased transistor count adds to the total power consumption, and which makes the power and thermal management more challenging operation. So there are various ways of reducing power. For instance, we can reduce the supply voltage to reduce power, or clock frequency, decrease the clock frequency to reduce power, the dynamic power. In fact, we can look at if we look at the generations of CPUs, we can figure that the most modern CPUs are operating at reduced voltage levels. So, however, this makes the design a bit more complex because the logic levels that determine between the logic 0 and 1 can be confused easily as the voltage levels that determine them, become closer and closer. So who controls these variables? Most of the time, the operating systems. But there might be other software that can be stored in memory and used to dynamically control these variables to minimize the power consumption, particularly at idle times. The last metric I'd like to talk about today is reliability. This metric is quite general and used with almost all electronic devices in the market because every consumer wants to know how reliable the product that they're buying at the particular price they're sold. This would also consolidate the comparisons that they make while buying a certain product. Reliability is expressed in terms of average number of hours before a failure or irreparable state arrives. Each product is replaceable, therefore, the system can be repaired by replacing electronic components. However, this process takes time. The time it takes to complete the repair job is known as the time to repair. After the system resumes normal operation, then the system becomes again prone, inclined to a new failure. The time it takes between failures then known as the time between failures. And these are random variables. So the average or mean time to failure is known as the MTTF metric. And average or mean time between failure is known as the MTBF metric. These are numbers. These are like the average of these random variables. If you search for these metrics on web, for instance, for hard disk drives or SSD drives, you will find plenty of information about how reliable these products are, and this reliability is expressed in terms of MTTF or MTBF. So, as a summary, although I touched upon the effect of transistor scaling in terms of cost and performance here and there throughout this slideshow, I'd like to summarize it for all the metrics we've discussed so far in this short video. First of all, the transistor scaling increases performance because, as we know, remember, due to Moore's law, famous law, as the number of transistors increase, the performance increase. It reduces the transistor wire delay and gives us more transistors with which to reduce cycles per instruction. It can reduce local power consumption due to the use of more transistors, at reduced voltages. However, this is undone by increased integration. In other words, by packing more transistors into a given silicon die area. And eventually it causes increased temperature problems. Increased temperature leaves the system at an unreliable state, and however, one of the cure for decreased reliability might be to add some redundancy to the system, to correct for errors. The way we can add redundancy is to add extra logic into the circuit, but this can only be accomplished by adding more transistors, unfortunately. However, hopefully, the added temperature due to the extra transistors can be offset by the increase in reliability. Finally, transistor scaling reduces the unit costs, but increases the startup costs. So you can see that the metrics are kind of affected in a complex manner. There's no straightforward way to tell the dependence between these four different metrics, while the transistors keep scaling every year. The choice of the design or for the architect or the designer. Before you design a system or an architect a system, for a given set of evaluation criteria, this becomes more challenging than it has ever been before. Anyway, in this class, we covered cost, unit and startup cost, performance, latency and throughput, CPU performance equation, power and energy metrics, and finally reliability. These are the four fundamental metrics when it comes to the estimation and evaluation of performance of a given set of complex systems. In the next lecture, hopefully we will start diving into the instruction set architecture, so-called ISAs, and trade-offs associated with ISAs. Please feel free to drop any questions you might have about today's lecture into my email box, and I'll be more than happy to help you with your questions. Thanks a lot.